Assalamualaikum to all. So today I will present or share my current research on hybrid nanofluids, which is magnetohydrodynamics boundary layer flow of hybrid nanofluid over a moving plate with Joule heating. So this is one of my works during my PhD study under supervision Prof. Dr. Norihan Muhammad Arifin and Prof. Ayan Pop. Okay, so this is the outline. Okay, so hybrid nanofluid is a new kind of nanofluids which is prepared by suspending different types, two or more of nanoparticles in a base fluid or hybrid nanoparticles in a base fluid. So this is based on review paper by Sarkar et al. In 2015. A hybrid nanofluid may offer a good thermal characteristic as compared to the base fluid and nanofluid as a result of synergistic effects. So this is based on a review paper by Siddiq et al. 2016. Okay, but for my study, on my research, so I will focus on numerical study. So we will test either the hybrid nanofluid is a good heat transfer fluid or not. Okay, depend on the situation. Okay, so this is a few of nanoparticles, types of nanoparticles and base fluid. Okay, so for my study, I focus on metals and metal oxides nanoparticles, which is copper and alumina. Okay, so this is correlation of hybrid nanofluids. So this is basic correlations of hybrid nanofluids. So the source is for single nanofluid is by Alsop and Abunada. So for hybrid nanofluid itself, so there are two main reference that I used during my study, which is Devi and Devi 2016 and Takabi and Salehi. Okay, for this work I use Takabi and Salehi. So this is nanoparticles and fluid properties. Okay, exact properties for copper, alumina nanoparticles and water as the base fluid. Okay, so objective and scope, for this particular paper, so first we want to analyze the hybrid nanofluid flow over a moving plate with MHD and Joule heating effect. So we want to investigate either this hybrid nanofluid is good heat transfer fluid or not for the case of moving plate. So if we have a fluid flow over a moving plate, and then we consider MHD and Joule heating effect to discover the control parameters which can delay the separation of fluid motion and enhance the heat transfer operation. Okay, for the scope, use correlations by Takabi and Salehi. Okay, and then we use copper and alumina water hybrid nanofluid. Okay, so this is the physical model. Okay, and then this is a few physical assumptions. Okay, so we consider the hybrid nanofluid with its velocity u over a permeable moving plate. So permeable moving plate ni we want to allow the possible fluid suction. So that's why the moving plate is considered as a permeable. Okay, and then we have equations for that magnetic field. Okay. So this is the similarity transformation process to convert the PDE. So our governing model, so in PDE, so the mathematical model come up from the physical model, and the physical assumption is in the PDE. Okay, but we can solve directly this PDE. Okay, so that's why we use similarity transformation to transform this PDE into the ODE. Okay, so from this ODE we can solve it using BWP4C solver in the MATLAB software. Okay, or a few researchers also use Maple, using shooting method, via Maple, or analytical method. But for my research, I focus on using BWP4C solver in the MATLAB software. Okay, so this is the physical quantities of interest. So skin friction coefficient to check the flow characteristic, and local Nusselt number for the heat transfer performance. Okay, so this is the stability analysis part. Okay, so usually, okay, for my research work, so the solution that we obtain so might be multiple solutions. So for example, for a moving case, okay, so when we consider opposing flow or um, so when we consider two different situations, so there are possibilities for us to get multiple solutions. So that's why we want to test so which one is the physical solution, either the first solution or the second solution. So we put the first solution for the solution which converge first, okay, which fulfill the boundary condition first. Okay, and then this is the results and discussion. Okay, so model validation is compulsory, okay, for my works. Okay, so we want to test either our result or our model is correct or not. So that's why we need to do the model validation. Okay, so for this work we compare a few case, okay, by Zainal et al. 2021 and Rohni et al. 2011. Okay, when PR equal to 6.2, lambda equal to 1, and Biot number approach to infinity. Okay, so we can see that the present solution is in accordance with those references. Okay, so this is the graph of our skin friction coefficient and heat transfer rate or local Nusselt number. Okay, so from this graph, okay, dual solution exists for the selected value of parameters. So we can see that the dash solution is the second solution. Okay, and the straight line solution, that is the first solution. Okay, so we can see that the second solution exists, okay, in limited value of m. Okay, limited value of lambda, sorry. So as m equal to 0 to 0.02. So an increase of the magnetic parameter extends the critical value. Okay, so actually we need to find this critical value so we can know that is this magnetic parameter can delay the boundary layer separation or not. So since this is a boundary value problem, so if this critical value is as the benchmark, so after this critical value, so no solution exists. Okay, so we can't use this physical model, so we can use the PDE. Okay, so we need to use full Navier-Stokes model. Okay, and then this is results for suction parameter. Okay, so this suction parameter, so we can see that an upsurge of suction parameter extends the critical value, means that this suction also can delay the boundary layer separation. And then both skin friction coefficient and heat transfer augment with the rise of the suction parameter. Okay, and this is the Eckert number. Okay, so Eckert number ni is a parameter that arise, okay, from the Joule heating process. Okay, so this Joule heating process produce heat from the electric current to the plate. So the increment of Eckert number may inflate the temperature profiles. Okay, but it reduce the heat transfer distribution. Okay, so another methods that we can use to check either our methods and model is correct or not is based on this profile. Okay, so we have velocity or temperature profile, so we can see that the solution fulfill the boundary condition. So the boundary condition theta so should approach to 0 lah. Okay, as eta approach to infinity. Okay, so we can see that this profile is fulfilled. Okay, so means that our model is correct. Okay, so this is the stability analysis for the first and second solutions. Okay, so the results from so we will test the stability analysis for the first and second solution. Okay, but for particular value of critical, for particular critical value. So for this test, we use critical value negative 0.367 975. Okay, and then we can see that all the smallest eigenvalues is positive for the first solution and negative for the second solution. So this affirms that the first solution is physically stable. Okay, and another thing is, okay, the eigenvalue approach to 0. So we can see that the eigenvalue, okay, as lambda approach to critical value. Okay, so critical value, okay, so we can see that both eigenvalues also approach to value of 0. So this is consistent with result from Merkin. Okay, and then this also implies that our stability formulation is correct. Okay, and then for the conclusion, the solution exists for the case of lambda less than 0. Okay, temporal stability analysis revealed that only the first solution is stable. Okay, so the stability analysis is like a compulsory method. Okay, if we find the multiple solutions, so we just want to assure that the first solution is stable and the second solution is not stable. So that's why we do the stability analysis, okay, for proving the solution. Okay, the separation of laminar flow can be delayed by enhance the suction strength and magnetic parameter. Okay, so this observation is based on the location of critical or separation value. Okay, so the augmentation of heat transfer rate is seen for the addition of suction and magnetic parameter. Okay, the rise in Eckert number not expands the critical value. So we can see from figure 6 that the critical value is same for all value of Eckert number. Okay, and then but leads to the increment of the temperature and slightly widen the thermal boundary layer. So the findings are only conclusive to this problem only, so more investigations are needed, okay, to observe the hybrid nanofluid flow. So for example, the result of these parameters, for example, suction, magnetic parameter or Eckert number, okay, maybe different, okay, for different situation. Okay, for example, this one we consider a moving plate. Okay, so the result may be different if we consider cylinder, okay, or sphere, okay, or stretching or shrinking surface. Okay, so this is a few reference, okay, regarding the hybrid nanofluids, numerical study of hybrid nanofluids. Okay, thank you all.